Okay. Thanks very much for having me. I'd say it's great to see you, but I can't see anybody with the lights, so please wave and tell me your name when you ask me a question. We're going to talk about computer-based interconnects from our perspective as Meta, and I will try and do a good job of creating some, I guess, maybe not FUD, but some tension with David's position from Nick's, and maybe we can arm wrestle about it later. I don't know that I need to go into much detail about the various use cases that Meta has. We have not only sort of computer-based racks, but also sort of these growing AI ML clusters, which will be the focus of the talk today. But our use cases are wide, ranking and recommendation, large language models now, generative AI. I think if you've seen the latest Meta Connect, and compute requirements across the entire spectrum there, right? So sort of compute vision in 3D and AI, ML, speech translation, we're moving to video, et cetera. So we think we have a pretty diverse set of physical requirements as well as IO requirements. I'll do my best to sort of focus in on where I think that discussion should happen today. This is sort of a chart which is becoming sort of like Chevrolet, right? Mom, apple pie, and Chevrolet, right? The growth of AI, ML, large language models is exorbitant, right? I mean, if you start to plot this over time, we're seeing that the model sizes are growing every 4 months, doubling every 4 months, which is sort of not something that I think we on the hardware side can really handle. I think and so what we did, what our buddy Rob did, was plot out the growth of various hardware-enabled sort of component growth over time. So you look here, you can see Ethernet bandwidths, we can see PCIe bandwidths, HBM bandwidth, as well as HBM capacity, all sort of normalized, right? We're just sort of seeing the growth over time here. The challenge, of course, is that it takes us about 2 years as an industry to double the performance. And you know, maybe even that's being sort of generous, although we try really hard, right? So here we are, falling behind, we think, where we need to be, or at least what the demands are on the system. And here's sort of a different perspective on that, right? Looking at the scaling of peak hardware flops and memory integration bandwidth, sort of telling the same story here, right? This is the so-called memory wall everybody talks about. We need more and more memory to deal with these larger and larger model sizes. We're not getting it from the component side. We're trying really hard on the architecture side to do that, but the challenge remains. So then the question becomes sort of, you know, if we're falling behind, what are we going to do? I think the answer to that is sort of an open question. Clearly what we're trying to do is create larger and larger clusters, make larger and larger systems here. But I think it's illustrative to sort of take a step back and look sort of at the requirement itself, sort of what is the IO that we're trying to move, why are we trying to move it? So here's a cartoon of a potential option around what a GPU system looks like. We can see here, I think of this in sort of 3 general realms of IO. I think we can all agree on this, but please tell me if I get it wrong, if you have a different view on this. GPU to CPU, that's really been taken care of in the recent history, or I guess the long-term history of PCIe, right? We're moving forward on PCIe Gen 4, et cetera, et cetera. Excuse me, it's going to move to a terabit per second, 16 channels of, you know, whatever the next line rate is. We've been, I think, done a good job as an industry driving the electrical connections out to the NIC that David just talked about. And we use some of that, well, we use that bandwidth for the CPO communication. The CPO often gives us sort of access to different levels of memory in the memory hierarchy that Michael talked about. NVIDIA, I want to call them out specifically here in the Grace Hopper. I should have maybe even referenced them, right? They've done something even more interesting and put the CPU and the GPU in the same package so that they can increase the bandwidth here. Increasing that bandwidth beyond sort of what PCIe can do, significantly more, has allowed them to adjust that memory flow and change the requirements there to some benefit at the system level. Then there's the GPU to GPU I/O. And here I'm throwing scale up and scale out together. This is the back-end fabric. Really, as we see it, they're the same thing. They move the same data. They're actually used in the same way. There's different sort of levels of bandwidth, more because of the economics around the interconnect itself than anything fundamental in the way that the data moves. But you know, it's pretty clear that there's a significant growth required on this moving forward. If we look at it, though, it's on the order of a terabyte now. Scaling, I think the goal is something always 50% gen to gen, so we want to see that grow over time. And current systems are supported with 400 G type modules, DR, DR4, maybe DR8, FR4 in our case, but some number of these 400 gig modules electrically routed from this package to a faceplate supports current current requirements. And then there's a question, of course, of scaling moving forward. Is CPO the right solution? Is LPO the right solution? I guess what I'm trying to say is I don't want to get into that because I think the focus of our challenge, I guess, for the industry, our call to action is going to be really the third area here. If you look at GPU memory, I/O here, and here I'm specifically talking about the memory moving to and from HBM, this is really a fast, low latency, low capacity memory hierarchy. It's right there, and so it captures a certain amount of the data that we do and a certain number of the transactions that we do on that. This is right now, point to point. I think we'll talk about sort of disaggregating that and sort of doing something in the memory hierarchy here to address the capacity issue. Maybe it goes to multi-point in the future. But I think the significant point here is that right now it's a terabyte per second at HBM3, so maybe HBM3 is next generation. The goal, again, 50% increase gen to gen, drives it to 1.5 terabytes per second, and then 2.2 terabytes per second in the very near future. This is sort of next gen sort of time frame. Bandwidth density, because we're trying to escape a lot of this bandwidth off of a very limited edge here. Economics around this, because what's the cost of a copper trace on a package? It's, I don't even think we could say pennies. It's going to be fractions of a penny, right? Power, latency, et cetera. All these things are a significant challenge here. So Ollie's out here somewhere. He'll tell me, why do you think you're going to get to 3 picojoules per bit, right? And this is why we need to get there, not why I think we're going to get there. All right, so really what does that mean, right? So let's look at the cluster architecture. Here I am talking about sort of these high bandwidth memory links, right? Where are we going to use them? If you look here is sort of a diagram we have together, a cartoon of what the Grand Teton server backend network looks like. So in this case, man, I wish I had a laser pointer. The scale up, so connecting, in this case, 8 GPUs together, is done with onboard traces. Right? Short, relatively easy to manage. There's a lot of bandwidth moving there, and so it's a difficult engineering challenge, but we solve the SI problem, we solve the cost problem, and then off you go. From there, 8 is never enough, right? We connect in our rack, 2 sets of these 8 together, create a rack switch. Those are done with copper cables inside the rack itself. Relatively low cost, sort of bandwidth lower than the scale up network because the copper cables cost more than the copper traces. There's a switch involved there. And then we go outside the rack. And as David, I think, said eloquently, outside the rack, it's optics. Whoever you choose to do the optics, LPO, CPO, retime pluggable modules, in some sense, it doesn't matter. You have to choke the bandwidth to make it cost effective to sort of move the data around here. In this case, if you're doing these across the cluster types of requirements, these things, this one went out of sync. Sorry, we're going to build right through here so I can talk about it rationally. Intra-cluster, so the bottom, right? Across the cluster is hundreds of meters. Right? We've, I think, publicly announced 16,000 GPUs in our largest clusters. Clearly, we're moving beyond that, as I think the industry is. The larger clusters go across data center buildings, so we're talking about hundreds of meters to sort of make that work. And that type of traffic is this GPU to GPU switched back-end fabric. It looks like an Ethernet network or an InfiniBand network. It's what we know and love today. If we start to think about what intra-rack looks like, so that would be sort of the next, can I get this down? You can't see that. Nope. You start to look at adjacent racks. Adjacent racks are on the order of 20 meters across a couple of racks. We have to go up to the cable infrastructure and sort of down again. It's never 2 racks next to each other. It's sort of a couple of racks talking to each other. So we're in this sort of 20 to 30 meter space. In that type of distance, you can be thinking about GPUs maybe talking to CPUs. I mean, that's a long way, right? GPUs to memory, certainly for a disaggregated system. GPUs to GPUs, obviously, and scale up. So that's the type of fabric or bandwidths and requirements we'll have. And then intra-board, really in the rack here, or close to each other as you can get, is going to be GPU to memory, disaggregating maybe some of the functions of a GPU so that we can deal with sort of the high thermal density and power density associated with these large next-gen GPU systems, and then potentially GPU and CPU, depending on what the requirements are for the GPU there. So when we talk about GPU to memory, which is kind of what I'm going to focus on in a couple of slides here, I'm going to tell you that we're looking at something 20, 30 meters with the types of bandwidths that meet this 2 terabyte per second type of requirement that we see happening in this sort of next gen for HBM. So I think Michael sort of pushed us a little bit to be a little bit more sort of 3 to 5 years out, maybe a little bit more sort of challenging to the industry. But we had a discussion this morning, right? What does it take to get sort of new technologies adopted? Don't shoot behind the duck and don't think, oh, the next gen, I can just get there and it'll be great, right? We have to be able to provide the performance required to meet future data center requirements, or in this case, AI ML cluster requirements, and be able to sort of target those so that we can build up the technology, validate the technology, and then finally scale it to volume. So here's my position, right? 2 terabytes per second. On the order of, right? I mean, if you tell me it's 2.03 or it's 1.98, I mean, that's in the noise, right? But this is where we need to get to, 2 terabytes per second, which is 16 terabits per second for point-to-point links, hopefully moving to switch or switch links in the future. Power consumption's got to be low. I mean, Ollie's right. It's not going to be easy to get to 3 or 4 picojoules per bit, but at 4 picojoules per bit, my 2 terabyte per second link is 64 watts, which is probably more than what the HBM is going to take, or depending on what the capacity is. You don't just get to keep on adding power to the GPU package and think that we're ever going to be able to cool that thing in any rational way. So 4 picojoules, I think, is the upper limit. We need to look at how we can drive that down. To Ollie's point again, and I'm sorry, I'm picking on you, but I think you get a really strong point. We're not going to get there simply because we talk about thin film lithium niobate. This is an end-to-end co-design. 30 meters is going to be a minimum. I think single mode fiber is going to take us a lot more than 30 meters. I don't think we have to optimize for 30 meters, but that's where we are. We talk about economics and everybody wants a target, right? Michael sent out a chart and said, tell me exactly how many, pennies per gigabit you can pay for. And I don't want to talk about that anymore. I think we need to stop talking about this, because I'm talking about 2 terabytes per second for a link, and we're going to take what? 28 terabytes per second, 200 terabits per second off of this package in the future if sort of this thing lands. And I don't want to talk about how many pennies that's going to be, right? We have to start talking about CMOS economics. And this is where, silicon photonics integrated on a package starts to become more compelling. If we're talking about dollars per square millimeter, as opposed to how many, photons or how many gates I have to do, then I think we can have a rational discussion about integrating this. But I don't want to talk about 5 cents a gigabit per second. Challenge me on that. I'd love to have that conversation. From our perspective as a deployer, it has to be high yield, right? I mean, we're putting an awful lot of stuff on there. We spend way too much money on GPUs as it is right now. We're going to put more on that package. They're going to be too expensive. We have to yield them at very high yield, and we can't sole source. I'm not going to say any more about that, period, right? We can't be in single-sourced solutions deploying millions and millions of these clusters at a time and then have to bid against each other to try and get the sort of capacity we need. It's going to take more than one vendor to get there, and we're going to have to be able to sort of drive interop to be able to make that happen. That's our challenge as an industry. Back to the point I was beating up on Ollie for there. Reliability, I mean, it's pretty clear that integrating more onto a package doesn't drive the reliability down, right? I mean, the reliability is going to get worse. The question is how much worse and how does it impact the system? This goes back to the end-to-end sort of design. We have to be able to design systems which are robust enough to the types of failure modes that we expect, which is very, very challenging. But at the same time, we can't go, I mean, Andy said this morning, 200 fit for a pluggable module, right? That alone is sort of disastrous. We have to be able to drive down the failure rates of these chiplets, these terabyte per second chiplets, into the single or low double-digit fits to be able to make this a rational design system. I think it's rational to talk about that, even though we're not here today, and it's going to take billions of device hours and deployed components to be able to get there. But the physics seem to support it, at least to my level of understanding. multi-vendor interops is going to be important, right? We don't want to be able to own, we don't want to have to own and deploy and design every end of every single link that we could deploy in these sort of composed systems for the AI clusters that we're going to build in the future. We really would like to see innovation on the far side, especially for these memory links, which means that we want to be able to specify, our GPU I/O, and then see a whole lot of innovation on the far side. That doesn't happen if we have to say you have to use this specific sort of optical widget that gives you exactly this, because then we're sole sourced anymore. Okay, I think that GPU memory is the challenge of the future. We're not scaling HBM bandwidth or HBM capacity fast enough to meet the demands of the AI model scaling that we're seeing today. Exponential curves always end. We're not going to scale AI ML, I think, exponentially forever, but we're only doing large language models now. We haven't even embedded sort of video and images into there. They're going to get bigger. There's no question that this is the challenge I think we as an industry and a community face. So there's a lot of work to be done here. Multiple parties and multiple domains. This is an end-to-end sort of design. FEC and latency and bit error rate and link level retry and power and thermal and all these things come into play, and we haven't even touched on sort of protocol or cluster architecture or software designs. We hope that we're contributing to this effort, despite the fact that I'm stirring the pot a little bit here. We've contributed to OIF. We support OCP moving forward, and we'd be happy to talk to you if you have questions, concerns, or challenges for us. Thanks.
Time for some questions.
Yeah, just want to clarify the 4 picojoule. That includes the host service plus the optics plus any external light sources, right? The 4 picojoule that you want 4 picojoule. And that's per one end of the link, not both ends, right?
Yeah, I want that 4 picojoules per bit to be everything that's required on the endpoint.
One endpoint or both endpoint?
So I'm going to think sort of transmitter and receiver, host side interface, and optical power supply.
So that's only one end of the link.
That's right, and 4 picojoules per bit for a transceiver on the GPU package.
And then also, what protocol? Would this be CXL or something else you have in mind?
I think the easy answer is I don't care, right? I want the best protocol that sort of that provides the benefit, right? We think CXL is a great protocol. It's moving in the right direction. It sort of meets, I think, a lot of the memory requirements that we would need. But there's a lot of requirements on this link that are more than what CXL is doing today, which we'll have to embed, I think, into the next generations. Yeah, thank you.
Hey, Drew. So I think within the first 3 bullets here, it's Brad Booth.
Hey, Brad, how are you doing?
I think within your first 3 bullets there, I think, we've probably heard enough people talk about the ability to get there. When I look at the last 4, though, to me that seems like the largest challenge for an industry, right? Because you want multi-vendor, you want people to be able to manufacture together, you want the economics of this, you want the reliability, all that has to fit together. I don't know who in this industry has all of that within their realm to be able to do it on their own without some serious consideration for funding by larger corporations. Any thoughts on how we address that?
Well, let me first say I think you're look, I didn't say 2 terabits per second. I said 2 terabytes per second. I haven't talked about the shoreline bandwidth density, but I need to get 2 terabytes over the same basically shoreline that I can get HBM out of. Yeah. So I need 2 terabits per second per millimeter. I don't know anybody who's got that solution today.
I'm not saying that it's
so
done today.
Yeah, that's fine.
People have talked about ways to get there.
Yeah. Look, I don't think we're going to get here because somebody comes up with this great sort of unobtainium solution with sort of barbed wire that comes out of it and bubble gum, and their special solution's good, and nobody else can sort of attack that, right? We can't, and I think it's important to realize, because at millions and millions of units, we can't deploy an unknown technology, right? So this is why, in some sense, right, this is such a great discussion, because we're not targeting next generation. We're targeting 5+ years out, next generation. We need demonstrations of the technology of the first 3 data points sort of in the next several years so that we can spend the next 3-5 years to get the next 4 data points after that. I will say from my experience in my previous life at a previous CPU company, right? When we launched that volume, we had done millions of units ready to sort of hit that volume and deploy it that day, right? The reliability studies, the economics, the yield, the manufacturability had all been understood before we released for HBM, which hasn't typically been the case for pluggable modules in the optics industry. But I think I'm suggesting that we need to move that way. Move to sort of known CMOS manufacturing assembly type processes, right? Chiplets have been demonstrated now, 56 different chiplets on a single packet. It's probably not economically, but it's feasible, right? Moving towards that, moving towards sort of known assembly and yield sort of issues. We're going to argue about silicon photonics or organics or the other thing and what their failure mechanism is, and we have to sort of chase those things down. But I have to believe that we're going to find a solution which is going to give us the reliability at the component level to get there. Now it becomes manufacturing assembly and doing this, millions of times. I can go on about this, right? I mean, I'm happy to, yeah.
Okay, I think we're done with the questions for this talk. Thank
All
you.
right, thank you.
Let's thank Drew.